All right, let's get started. Again, it's been such an incredible day of science, to be completely honest. And any minute I speak is one more minute I take away from all this awesomeness that's been happening. But I still need to introduce Professor Venkat Raman. So he's a professor of aerospace engineering here at the University of Michigan. So he got his PhD from Iowa State in 2003, and then he was at Stanford for a couple of years as a postdoc. And then he was at the University of Austin from 2005 to 2014. And then he made the right decision to come to the right place finally. And we cannot be happier to have him, because anytime we require advice on anything related to scientific computing, Venkat always has crazy ideas. Sometimes it's the right type of crazy, and sometimes it's just crazy.
Okay.
But I did want to give that context because he works on a lot of different topics, even though his area is applications for propulsion. He works on multi-scale modeling, he works on high-performance computing, he works on data assimilation, some machine learning as well. So he's very well-versed with computational science, high-performance computing, and scientific computing in general. So it's the best person to lead this distinguished panel. And I will stop talking and let Venkat take it away.
Karthik, thanks so much. I think it's incredible to have the support from MIGD for all these years. This was fascinating listening to all of you. And I'm trying to condense so that I can ask, I have so many questions for each one of you, and it can just devolve into that.
If I can say one thing.
Yes.
So that I have to say, I'm sorry.
Okay.
So the panel's supposed to end at 4, and I know at least Amitava has a constraint, but there is so much great discussion that are happening. So you can leave slightly earlier, but I believe we'll be talking beyond 4 o'clock. There's just so many interesting.
He said he had a Zoom call. He could just do it here. We could just join in.
That's true.
Now, I also want to say, if you're in the audience and you didn't get to ask a question, or you have something pressing, we will leave some time in the end so that you can also ask questions. But keep it at a higher level so we can all learn from this. Like the question about zeta scale, that was very interesting. I was going to ask this, and someone stole that from me, right? So that was pretty cool. So I'm trying to condense, like I was saying. And, there are a few things that come out of it from each one of your talks. And so one thing I learned from Amitava's talk and Christiane's talk is that clearly HPC in the current form, Frontier or what are the new machines are, have really changed how you think about computations or what can be reached. But I also wonder, if you just keep going down this path to zeta scale, and I don't even know what the name is after that, would it help your field at all?
Okay. Oops. Let me start. Yeah. I think Frontier is a game changer, and I guess it has even and DOE. I use this as an example. Had kind of really 5-10 years ago even thought about that that Fortran and OpenMP, Fortran, MPI isn't probably cutting it. OpenACC was tried, and they didn't get the performance, was too unstable and too buggy, actually. So, when they invested in Cocos, and this we talk about maybe 6-8 years ago, this was a real vision that they had, that they need to do it now to be ready today, when the Frontier and other machines have the GPU capability. And now I think they see the big payoff. Yeah, I think whether Cocos is the last word, I don't know. We might see even more advances in these libraries, but I think it's the right path to go to even zeta scale. Right.
Amitava, do you have?
So one of the slides that I presented during my talk had to do with the fact that fusion was hungry for the exascale. And I made the case that if you look at how fusion is evolved, the size of the machine available has determined the amount of physics that we can actually do. And what the exascale made possible then is to actually do a problem at the scale of a very large experiment, namely ITER. But if I look at outside of fusion, say in astrophysics, where scales are so much larger, and you could ask, would any level of computing ever be enough? And I think that we have to start worrying about something else, which is that computing is very expensive. And you have to ask that the people who are paying for it, at what point will they actually say that you're making progress? And I think that the question is going to come back in a different way to us. They will quickly realize that we can never claim that we can do a black hole or a neutron star in its full size. And they'll come back and ask us, well, can do all that complexity. Is there a laboratory experiment which you can absolutely model with absolute precision, including system size, parameters, and everything? Can you predict what that laboratory experiment done with absolute accuracy? And I think that question will be asked of us so that we can make the case that the kind of computing we are asking for, where we are asking people to allow us to extrapolate, is credible.
That's a good point. That's a good point. So it looks like, if I look at differences, I was talking to you before this, I work in turbulence, let's say, which is vastly simpler compared to the physics that you're handling. And so just like we have this notion of quantum advantage or quantum supremacy, we reach this idea of using HPC to its fullest capacity or capability at the petascale level. And beyond that, this question gets asked, like, what if you have the exascale machine, and if you run this huge calculation, do we really learn anything from that, right? So that question gets asked. But, you talked about people who pay us to do this research. We have somebody who does this here. So Fariba can tell us, is this HPC useful at that level? How do we, or what do you see from your viewpoint?
I was trying to, I was mentioning that given the limited budget that I have to also limit the scope. And in fact, I did say that I do not take on any projects in HPC. As you know, my PIs are users of HPC. In fact, sometimes, the facilities they apply for sometimes are the DoD facilities, DOE actually, if they're in the grant. So given that my level, certainly I can see, I certainly have heard the impact of, in some ways, HPC computing at this, call it extreme scales, has had huge impact. But my philosophy about computing, computational math, it's a little different. Because for some of the scenarios and for some of the problems that I'm looking for computation, I'm actually computationally constrained. So I know that you've been asking me, so why do I suddenly say that for something as in a grand scale of digital twin, I'm actually saying HPC is not the answer. Maybe I just say it's not the ultimate answer or it's not the answer. And I think what I'm saying is that, in fact, I've been telling people that given what I'm capable of handling in some sense, I'm looking at computation and algorithms that are basically aware. They're aware of the computational cost. Let me just say that. So I really have to modify what I said because you were like, say, oh, no, I'm not going to look at any HPC.
No, I think it's not
and we're looking, for example, seriously, I remember your presentation, we were talking about this digital twin workshop, and certainly for climate, and also others. We're saying about that, how about the biomedical, the level of computation you have to do? Certainly you need that. It was just that, for me, if you notice, I'm working on, for example, reduced order models or uncertain quantification, other aspects.
So there's more than HPC in computation. There are other ways.
Oh yes, I think we all know that. It's just that I said, well, DOE is taking it on very well. Let me see what I can do.
I was asking Amitava a more philosophical question before that. If let's say you were given all the computing power and you could solve this entire fusion reactor and you're done with it, would you trust those simulations at that point? Or these models, for instance, she has this coupling between the core and the edge models, which is a model, and same is true for you also, Christiane. And so once you go, and you made the statement, just increasing resolution is not going to solve the problem. So maybe I can get to millimeter resolution, but does it mean the problem is solved, or now we will question something else? And I think,
But it's also related to incomplete knowledge, how cloud physics, for example, works. Yeah, so we are not even certain what the right equations are. So yeah, no, there will be always problems regardless of scale, and the coupling problem I didn't even mention really, between the ocean, the ice, the land. That's even first order, maybe zeroth order in some of the modeling efforts. And you can have all the accuracy in your atmosphere. If you couple wrongly, all the accuracy is gone. So there are many more layers of complexity that I didn't touch upon.
Okay.
Maybe also, we talk about HPC, yes, but I think the data issue, more and more data this is a whole can of worms, open can of worms, which I don't think we have an answer to, how to deal even with data.
This is something to discuss as well, so we'll come to that. Yeah, that is a very important point also. So I want to talk about the hardware itself, and because we have experts here on the computer science aspect and the hardware. So we say heterogeneous machines, and I think 10 years ago, if there was a GPU, I would have said, I'm not going to use it anymore, but now we're all very comfortable with that. But there's a lot more heterogeneity in the world, right? So you have wafer computers or neuromorphic computers, or if you have digital twins, you can have things, some of the operations on the cloud, some on local computers, some on HPC. Is there a thinking about how to deal with this kind of heterogeneity from, for instance, in terms of how the software is developed, for instance? I'll let Alex take it as a computer scientist.
Yeah, sure. So first of all, I think there are, like you said, there are many proposals for new kinds of accelerators, and this is the way things are going to go. I mean, you're essentially going to see people proposing to accelerate certain aspects of computation, certain classes of algorithms, and the challenge for all of those technologies is that there's a bunch of accelerator companies that are already out ahead of them with established markets. So we're adding accelerators all the time actually today. You don't realize it, but maybe. But your GPU today is very different from the GPU of 10 years ago. It has tensor cores in it, and it has ray tracing accelerators, and who knows what else is going to be put in there when it proves to have a market down the road. So accelerators are getting added all the time. They're currently being hidden behind interfaces. I think it remains to be seen how much that'll be unbundled. I think to the extent that applications need more direct access and fine-grained control, then that will happen. If it can all be managed at the interface level and people are happy with that, then it won't. But I think this is the future's already here in that respect, right? So.
From other kinds of architectures, like quantum machines, for instance, how do these, there are all these codes developed and problems developed and so on. Where do you see quantum machines or these kind of architectures fitting in, in the kind of applications that we have seen here?
Yeah, I mean, I think a lot of people starting to realize that, it's really this classical and quantum interface that's really important because, our quantum computers are controlled by classical computers. And so there is always data going back and forth. And, there are some things that are going to be way better done on a classical computer. A quantum computer is not going to help you download YouTube videos of cats and such and any better. So, there are tasks that really should be done classically. And so, what does that look like? And how much, and also sort of, how much classical computing power at what level, right? Right now, from the hardware perspective, we have to have real time, right? Our classical computing is doing things real time while we're still holding the quantum memory. These processors got to go fast. They've got to process the data coming in and then just make some decisions and act on the qubits. But there's also another layer where you can finish your computation, take the data, what do you want to do with it, analyze it, and then put in another calculation in, sort of on that variational quantum eigensolver level, and these various techniques. And so, then that doesn't have to be real time. And so some people are building that as well. And so what's the whole picture going to look like in the future? We just don't know. I think that it's a very interesting. We're exploring that. And some people think that maybe a quantum computer should be sitting right next to an HPC, and just some things are farmed off to a quantum processor, and some things are better done GPU, and people are used to that.
So this is a little bit even more heterogeneous than what we're talking about. Right now, we have CPUs and GPUs sitting on the same, Amitava was talking about walking into a room and seeing frontier. Will there be a future machine where there is no single place where the machine is? It's everywhere.
Well,
right?
I think there's always communication time, right? That's really, really important. Like, that the time is very precious while the cube is sitting there decohering as well. So, there are people talking about using GPUs to actually do some of that real-time calculation much faster. We just don't know. I think there's so much space to explore there, and where people are just starting to play around with how to architect that.
I think as I said before, just to build on that question, ultimately the real cost is energy and the money to power the electricity to do all this stuff, right? And so that means that to get low power, things have to be packed into small spaces so that the things are moving short distances over without long wires. And so I think for these very, very expensive calculations, they will always be done in a relatively confined physical space.
Okay. Doug.
Two comments on heterogeneity. So last June, we issued a RFI, and we got 49 responses from vendors. Classical, US HPC vendors, AI vendors, they're out there, quantum and cloud, okay? It is the Wild West right now with regard to heterogeneity. I think that's a challenge, but also an opportunity. Right now, with chiplets being designed to do virtually anything and everything, I think we have the ability to say, okay, we want to design a node that makes particles really go. So we're going to do this, and this, and I think we're going to be able to mix and match. So I think we're going to go to more and more heterogeneity. I think we're going to be able to have more ability to kind of control what that looks like. The question then for the next system, is it a large monolithic system that's intimately connected? There's good reasons for that, where every node has differences, but they're all the same, kind of like Frontier. Or do we have a monolithic system that's intimately connected where these nodes over here can really do AI, these nodes over here can really do PDEs? Okay, we're certainly looking at those sorts of trade-offs.
Right,
So,
which is a slightly different view from these bigger blocks, right, of neuromorphic or wafer or quantum, to go to say, I want to solve Navier-Stokes equations. Can I design a chip that is very good for that? Yeah?
Now, the market, of course, is driven by AI. So with regard to the voltas that came in Summit, we really didn't know until the last minute that, hey, there's a MMA operation that's really fast for 16-bit, okay? Matrix multiply, accumulate. That was a surprise. So what did that mean for PDE folks? It really is, we then, in an ECP, that's been true, we've been engaged in hardware-driven algorithm design, okay? We've been able to show we can use those tensor cores, and we can cheat and use low precision and iterate to get the 64-bit answer if we need it. I also think as a community, we've gotten lazy and complacent. We just say, okay, I need 64-bit everywhere, okay? We need to figure out how to use 16 effectively, maybe even 8. Now, there are good arguments as to why maybe that's just not possible. But I think, accelerators are here to stay, and it's going to be really interesting watching it move forward. With regard to quantum, I'll echo your comments. I see quantum as another accelerator. I shouldn't be so cavalier about it, but our colleagues in Japan and Europe have a quantum classical system connection on their milestone chart, essentially for the next year or two.
Okay.
And we could argue maybe it's a stunt, but we need to understand that interplay. And certainly, if you need to drive hundreds or thousands of circuits, you need to have low latency, maybe a millisecond or less, and so they are intimately connected. And so I think there's a big role for quantum moving forward. The question is sort of when and what. So.
Interesting. So if you look at these programming languages and how we are developing or how we are accessing these machines, the points made at different times during the talks. There's a difference, right? Before we would write each research group like mine, we would write codes for a particular CPU. They may not be very optimal or things like that, and we'll make it work. Now it looks like many of these new systems, you have to leverage COCOS or these lot of acronyms, or Legion or things like that. Is there a danger that we do not know what goes on there, and that can lead to more, because if these computations are expensive, and we're using these tools that are also, sort of evolving scientific products, how do we manage that complexity? Like, you've been part of, Alex, you've been part of the PISA program and so on. Is this something that comes, a verification of this task-based parallelism, what they can introduce and so on, what errors they can introduce?
Well, I think there's a couple dimensions to that. I mean, we can talk about performance and we can talk about correctness. And so first of all, on the correctness side, I think that there's a huge open problem about verifying the correctness of HPC codes. And there's still a bit of a cultural gap between people in the classical computer science verification community and the HPC crowd, even to talk about this. They use different language, and the words mean different things, and I've had problems with those conversations over the years. But I think, when you have very complicated systems, especially systems that are composed of pieces that were written by people who don't know each other and maybe never even met. I mean, you're using libraries that were written a long time ago by people who are far away and maybe had different goals than you think they had. There's a real question of whether you're getting the right answers, and there's a need for ways to check that go beyond testing, because testing is not a very strong methodology. And and verification work is mostly gaining traction in other parts of the software world, but that is happening. So one thing I guess people might be interested in is that there are places where software verification, full verification of correctness, is commercially viable, and people are building tools and making the investments to do that. And so I think that that as that comes out of the labs and gains more momentum and has more investment, it will start to be used more in the HPC community.
So you think this is only like a cultural gap, but the tools exist, or that there are?
No, there are also technical problems.
Okay.
Right.
Okay.
I think fundamentally there has not been nearly as much attention paid to reasoning about floating point and the kinds of approximations that are made in computational math as has been paid to the discrete side of computer science, of programming. So I think there's a research program there as well that is partly a product of that cultural gap, I guess.
Certainly.
So on the other side, there's a question of are you getting the performance you should get? Like maybe I'm doing something silly and my program could actually run faster if I just made some small changes. And it's very hard to know. It's actually really, really hard to know. And this is as hard a problem as the verification problem, in my opinion.
But do you think these libraries actually help you in dealing with this, or are they just another layer that you have to now understand?
They're just another layer when it comes to, actually, if you really care about the ultimate performance, they're another layer. I'm not saying they do a bad job. Okay, it's just that whatever decisions they make tend to be generic decisions that may not take advantage of domain-specific knowledge of your particular application. And so we need really good tools for this too. And people are working on this, but it's a hard problem.
So, Patti, I want to ask about this. So your field, compared to what Alex is talking about, it's very nascent now in terms of, so are there special things that you're dealing now so that you can overcome some of these gaps in traditional HPC areas in terms of coding and programming and so on?
Yeah, it's like the whole programming language is something, kind of have to be invented, and, there academically usually it was done, and then IBM, when they started their commercial system, they have a lot of, they have that OpenCASM, which is a really good language. But as things evolve, it's not insufficient, right? We find out, okay, now we have to add extension, it just doesn't work well. And so it's a research project of its own, but it's a little bit of a chicken and egg problem, because until you have the hardware and you're running these things, you won't know what you need to do. And so people can have lots of, there are a lot of great academic work, but until you hit the real hardware, then that's kind of a very hard thing to figure out. And it's great because there's a really rich community out there. For example, I said we have the ticket compiler that actually takes input from your programs from any language or any language that we know of, and then it compiles to any hardware that exists out there that has a standardized input that it accepts, and we're constantly updating that and constantly improving it. IBM has a Qiskit, also has a similar type of compiler, and you can benchmark which one works better. You run it multiple times, and people are even mixing and matching and say, run it on Qiskit and Ticket, and then sometimes you might get a better answer. So those things like people are trying to figure out, right? And it's a lot of fun. We don't know. It's Wild West out there, but it's exciting.
So Doug, along the same lines, like you showed this plot where you said some people are writing the core code because they don't want to use the libraries and others use it. So as it tilted over the years, like that you see now that more are relying on Cocos and perhaps software like Legion, rather than writing from scratch a GPU code or things like this.
Well, yeah, with ECP, we've got a bunch of teams that know the hardware really well, okay? And so we're kind of in a bubble, so it's been different than what Alex said in that we've got very good performance with Cocos, but it's because the teams go in there and they say, I'm going to program on the metal, I'm going to do OpenMP, I'm going to do Cocos, I'm going to do Raja. We got mini codes that have multiple options, and these middleware layers do as well. So what they've seen is they pound on these things to where they get the same performance basically with these layers. So what we've seen is the layer has very little performance hit, if any, but it's with teams that are really experts. And then you need somebody, at least one person on the team, that really understands the hardware and understands the compiler. And so, I think that ECP has lowered the barrier to entry and de-risk a lot of things for other applications, but it's still a contact sport. You're gonna you still have to really understand, how things are done. Fortunately, with GPUs, AMD did a pretty good thing. They said this CUDA stuff in NVIDIA, if you can't fight them, join them, right? I'm going to make HIP just look pretty much like it, okay? So porting from NVIDIA to AMD in most cases took hours, but getting the performance took much longer, okay? The point, what I've seen with NVIDIA to AMD to Intel is the biggest challenge is conceptually thinking about how do I have to occupy these GPUs. I've got to break up my loops. I got to unroll kernels. I have to have lightweight kernels. I can't have divergent kernels. Once you go through that, which can be onerous, at least for the current class of GPUs, you've solved about 80 or 90% of the problem.
Okay. So now when the Intel GPUs come out, will we again have the same issue?
And that moving over to that GPU is still is not that hard.
Okay.
Conceptual challenges have been overcome with the first set. But what do the next wave of accelerators look like,
that's
right?
Yeah.
And so in the end, you can't, it's a multidisciplinary problem. You really can't divorce yourself from knowledge of the hardware and knowledge of how the compiler works. At least somebody on your team.
Absolutely. Amitava.
Doug touched upon this already, but I have a concern that I should raise, that I know his concern too. At least in the fusion plasma community, the exascale has one project, and the people in it, say about 35 people, are steeped in a culture that has been created by the exascale project. Most people in the plasma community do not understand what the exascale yet offers them, because if you are fortunate to be part of the program, you learn a lot. And most of them don't know how to adjust their legacy codes to take advantage of this. One of the things that I'm worried about is that we are not educating people fast enough. And this is actually a deeper issue, because the way we are teaching people computing, and there are people in this group who have much more knowledge of that than I do, but the way we are teaching at least the standard computational physics course in astrophysics as plasma physics does not prepare them the textbooks that we are using are unsuitable for the task. And yet we have this revolution going on, and we have to educate the public. I just mean the educated public,
That's right.
by large, not just a handful, on how to take advantage of these computers. I don't think we have solved this problem at all.
I think that's a good transition to my next question. Is it how does this impact education and training the workforce, right? So this is extremely true. I mean, even if you look at any undergraduate program, the notion of computing itself is not that strong, and certainly not high performance computing, right? And writing codes, writing good codes is very rare, you know. So I don't know your experience, Christiane. We are in the same university, but different departments. So what do you think?
Yeah, this is an excellent question, because I think we as educators in the sciences, we cannot do it, and we rely on, luckily we have a Michigan program in computational science, and we can send students to other courses and they get credit for it. I think this is a crucial component. I'm not even certain that we do it enough. So yes, we probably get the rudimentary training in GPU technology and OpenMP and MPI. But I think there could be even more from a hands-on perspective that's conveyed. I can't embed any of these concepts that I talked about in any of my classes that I teach in the science. So yeah, I see this as I guess I do it, of course, in the background with grad students, just in personal meetings, but that's not to scale. And I think that brings up an excellent point. We are not doing enough in this country. Also, I mentioned briefly in my talk, I really see a need that to embed even more software engineers into our frameworks or into our workflows, even bring them into the science disciplines to help us with these code bases.
I'll add that, I mean, I saw this with Brendan and others in Castle. The best way to learn how to write good code, it's a team sport and a contact sport, is to sit down with somebody who knows it and to learn how to emulate good code. And so learning the syntax and taking a course isn't near enough.
Yeah.
So I've seen students spin up over a 10 or 12 week period if they're paired with the right person and the right code base. And so it is, I mean.
But how can we scale this up, Doug?
Well, I was just going to say, it doesn't mean it's easily doable in a university setting, right? But I know we can do better.
I will say this, the OLCF and ALCF, they have hackathons. And sending your students there, that made a step change, at least for my group. So there are incentives like this to do. But I want to go to Alex. I mean, so computing and computational science is different from computer science. So how do you deal with it in computer science? Like the computer scientists here, they won't listen to us about these kind of things. You know, maybe JB is the only one because he's in our department. But
Let me first say I don't have any cred with the computational scientists, but I've hung out with them for a very long time, and so I think I understand their worldview quite well. And I've been hanging around the DOE for long enough that I think I have at least some perspective on it as well. I'll take a slightly contrary point of view. I don't think this is a solvable problem. Okay, I don't think this problem is actually going to be solved. So I think everything that I said was true. And if what you need is to train a relatively small cadre of elite teams to build these kinds of things, these approaches will work fine, and that will meet the needs of a certain class of institutions. But if you really want something that's going to be used at a larger scale, people mostly have to teach themselves, and that means there needs to be and will be, at some point, a great simplification in the way we program these machines. I think it is absolutely inevitable because you cannot keep piling on new technologies. You cannot ask people to also learn to program quantum machines in addition, by hand, in addition to learning all these other things. And then you throw in some other kinds of accelerators, and every year you add some new technology which has its own programming model, which is incorporated with everything else. I mean, this is just not going to work, right? It's, people don't live long enough to learn all this stuff.
You make the case for the libraries now, yeah?
Yeah,
I was going to say that.
Well, there are going to be higher levels of programming, which will be the things that are taught. Okay, whether it's libraries or languages or whatever, that is, I think it's inevitable that this is what will happen.
That is a contrary view. I've been waiting for the magic compiler, Alex, for 40 years. So I know that wasn't what you mean.
But I didn't say it was going to be good.
Oh, well, okay.
Right. I mean, I think what it's going to be, you're going to have a transformation where the productivity of the programmers is more important than how well you're utilizing the machine. And most people will be satisfied with good enough. And then there'll be a smaller group that needs to get to that next level, and they will be the
You're right. I think better is the enemy of good enough. And I think people's time is much more expensive than the simulation time, right? I totally agree.
But this is a bit of a change of culture for some parts of the HPC community, I think. Yeah.
But it's not monolithic. Like there's also like, for instance, the postdocs that you guys hire at DOE labs come from the PhD programs we have here, writing simple enough codes and so on, not exascale codes. But if these students are now using the exascale codes to do their work, they lose that ability to write even those basic level of abstraction. So there is you create a gap by introducing the libraries, I think. You're taking out some skill set.
But let's the problem's actually a little worse than you think.
Okay.
All right, because we already have the problem today, all right, in that there are groups who feel very strongly about programming to the metal, insist on doing everything themselves, and their code still performs very poorly. Okay, so they're both unproductive and they don't get very much out of the machine, all right? So we can at least solve one of those two problems by kind of raising the level a little bit.
Okay. That I would say is an optimistic view, So before I transition to the next question, I want to see if the audience have anything to ask. You can raise your hand. Okay, all right. Go ahead, Ted Raker.
Okay, Todd Raker from ARC. So over the years, I've been involved in supercomputing for 30 plus years, started as a graduate student. And the new paradigm, machine learning. And if you go to the poster sessions, a huge number of students are using machine learning to bypass certain aspects of their modeling. Oops, sorry. So I'm animated, right? So I know the risks. I think in my head what that is. And to me, basically, to a certain degree, we're throwing in the towel. We're not going to try to implement the right physics into clouds, right? We're just going to do machine learning. It's going to guess. We're going to input stuff, and it's going to kick out a number. We don't know why or how, but it happens. From your perspective, from each of you, what is the risks that we have in doing that and throwing in the towel? And I'm not talking about overlords, right? It's the basic science. It's the computing paradigms. It's the hardware, software.
Can I take a crack at this? It's also a favorite, it's a great question that you pose for us here. And I hope I won't take too much time.
I got all day.
But
No, you don't.
the rest of you don't. At the level of science, I want to make sure that that people here understand what I am not saying. Dreams of a Final Theory by Steven Weinberg says, if you understand Schrödinger's equation, you understand the universe. That's a linear equation, for those of you who know quantum mechanics, and is solvable by many techniques. And I'm oversimplifying Weinberg just a little bit, great man that he is, or was. But I never believed that physics was like that, because I believed more in Dyson's point of view that the universe is nonlinear, that you don't have to always go to Schrödinger's equation to build up how clouds form. So there are levels of complexity then at certain equations that we arrive at. And in a way, it has to do with Venkat asking me, when you say first principles, what do you mean? And I'm not going to debate that point. Let's assume that a community knows what the basic equations are. I think it is foolhardy to think that you can just put the equations on a computer and you will never solve them for nonlinear problems to the degree of precision that you need to fully figure out whether the results you've gotten are reliable or not. And this is where the ECP culture of having applied mathematicians holding your feet to the fire on simple problems to say, on this very simple problem, what is your methodology predict? And I'm actually saying that every point I see a need to go back to the foundations. And I would like to reiterate to you, I'm very excited about machine learning, but I do not completely believe in machine learning unless it is backed up by intuition and mathematics of a kind that I can actually understand or solve. So may I just say, therefore, we can't throw it all out. The answer is not just more resolution and higher, more and more simulations, but I repeated return to the roots so we can actually make sense of what we actually get out of these codes.
Doug?
Yeah, I for the most part agree. So in ECP, we're exploring it somewhat skeptically, but exploring it to accelerate and augment workflows. Wherever we can automate things that maybe are a little mundane or easier, fine. You know, we're, for example, subgrid models for turbulence. Okay, maybe we can have an inference engine that can do things there. But, you know, again, for it to be at the tip of the spear and replace a simulation-based model, no. I really don't believe that's where we need to go for most of our domains. But I will say that, you know, we need to have our scientists have this in their toolkit and kind of know where it works and where it doesn't. One of our former lab directors said to me, Doug, I don't believe in correlations. And okay, that was his view. Okay. The other thing too is assurance. What and explainability. What is a model telling us? How does it get to where it is? Where's the cliff where a cat becomes a dog? I mean, there's a lot of concern about assurance as well. But I really wanted to see our workforce be trained up enough to kind of be able to be at the adult table and say, yeah, but, okay? So I think we need to be engaged and use it where it makes sense.
Alex, did you have something to add?
I agree with all of that. I think I'll just add that I think we're in an interesting historical moment, and that's part of what's going on. Is that, you know, we're in a transition from people didn't know about AI to AI can do a lot of things, and people have a hard time, I think, correctly gauging what it can do. People tend to be either very over enthusiastic or too pessimistic. Yeah, and so it's going to take some time to figure out exactly what the role is and what it can do well. But I think, you know, the current hype and the idea that it's going to, you know, people are going to use it for everything, I think like was said, I mean, you know, if you, a probabilistic notion of correctness, that's built in at a very fundamental level to these tools. And that it can only do what, you know, what's in the data, and that just isn't good enough for a lot of these problems.
Okay. Did you want to add?
Yeah, I would just want to say that, you know, a lot of people are actually applying these machine learning techniques to quantum, right? So, you know, we have all these skates that we're trying to calibrate and get the errors down. And people have shown that some of the machine learning tools can actually do better than humans and some machines. We haven't done so because, we've been making huge amounts of actual hardware and software improvements. And to us, it's more important to know where the errors are coming from so that we can go and address it at the hardware level and improve that than gaining a short-term gain, right? It may be better now, but we have no idea where the errors are coming from. We have no idea why. We have no idea how. And there's no way to go and fix it and improve to the next level. And so for us, it's more important to do that. Not that we're certainly open to like machine learning options, you know, when we run out of ideas to improve. But that's a limitation we see. That's a huge problem for sort of long-term progress.
Maybe when I can add to that, in the climate science, I think we have seen one, I would call it success of machine learning. So radiation codes are actually really well calibrated. We have extremely well measured spectra from solar radiation. And this is a place where machine learning is actually competitive in comparison to our physical models. So we have been seeing some successes where machine learning radiation codes were embedded as surrogates basically into codes, into weather codes. And this is important because the radiation code takes about 50% of time in this physics package that I mentioned. So this is a real time saver if we can do this successfully. And with radiation, it seems to be over short timescales, I should say.
Fariba, did you have anything to add?
Like a question, so, you know, from the panel, because let's say in computational mathematics, actually this term was, could say that maybe the scientific machine learning that's been, you know, from the older workshops that DOE Oscar had. So this has been now, I mean, it seemed like at this point it's very difficult to even find a proposal on anything when it has to do with modeling and computation of a complex system where scientific machine learning is not, I mean, some people consider it maybe some form of even hybrid modeling. where, it's sort of combining whatever physics known and with whatever that is not known, and maybe use data in order to learn the models. So I've seen the community going from basically in the beginning not knowing what even as you were saying, not knowing what machine learning or any kind of there was a little bit of I have to say resistance to any kind of data-driven modeling to, I have to say at this point maybe fully embracing it. And I'm not saying that it's because of the funding agencies, but I think we are all just seeing it, that it's been effective. And so what are your thoughts? I mean, you, for example, you seem to be a little bit.
Well, scientific, no, well, I'm not necessarily negative. Let's just be careful. Scientific machine learning is a loaded term. So on one end, we've spent a long time in the DOE trying to figure out how to make, linear solvers scream. And so if you look at, stochastic gradient descent, it's just another linear solve. And so one aspect is there's fundamental mathematics and computer science that could be applied to make this stuff really scream. Okay, I think, and most machine learning that I'm aware of now is linear. And I first was exposed to this in the late 80s where, maybe it was 9 or 10 nodes. YC Lee at Los Alamos was doing nonlinear. So there's a lot of theory and understanding that we don't have. And so that's more foundational, saying, okay, I want to understand the math and the theory behind this and make it better. And then on the top down, can I use a PIN, a physics-informed neural network, to have a better Navier-Stokes solver? There I'm more skeptical. Okay, yeah, I can maybe learn from other simulation outputs and then just sort of replicate what it sees, but to me that's not interesting or frankly credible. So
I think the fundamental challenge is, you have one world where you have, so hard constraints. So essentially equations like conservation of energy, things like that have to be conserved for your solutions to make any sense. And on the other side, you have techniques that say, 96% is good enough. Okay, and how you resolve that tension, and incorporate them together in a way that makes sense. This is the fundamental problem.
I'll go one step beyond this. I think typically when we talked about being, too much in your bubble, particular physics, and when you're in a bubble, you tend to think of the same kind of methods to solve problems. What machine learning does is just slaps you on the face and says you can look at it differently, right? And that itself opens up a lot of spaces. And for instance, 15 years ago, you cannot build correlations and call it a model. And now we accept it to some level. And then it forces you to think, okay, maybe it's not that bad. What else did we think is too difficult? But it's actually not, things like that. So maybe it's just a way to look at the problem, but it's not, bringing things the way it's hyped up to be as possible. Okay, so we have only a few minutes. So I want to leave with one question for each one of you and your thought on this. 20 years from now, what would HPC look like? Or 50 if you're daring.
Again.
Well, I'll be retired and hopefully a scratch golfer, so I'm not sure I'm going to care.
No way.
I forgot this is recorded.
I think seeing Zeta scale would be awesome, but I think we see more and more cloud computing.
Say for quantum, a lot of people are comparing us to ENIAC right now. And that's probably appropriate, and it's like being when we built the ENIAC, trying to imagine what it's like today with our cell phones and whatever devices around. I think we have no idea what that's going to look like at all. I think it'll be exciting to find out.
Fariba? You're going to pass this question. You have to.
Actually, I'm thinking about, because as I've been mentioning that, yes, I kind of try to stay away from HPC, but I think something about computing. I think, first of all, I'm trying to be more positive about maybe some of the use of AI in scientific computing is that it has democratized in some ways computing and has made computing also a lot more available in fields where, because it was hard to do the computing, now they can say, well, okay, I can just write a code, and use my, basically PyTorch. So that aspect, I think, is that's really nice. So I think computation in some ways and our interaction with it would be something that it's going to be a lot more prevalent. And it's kind of interesting. Okay, that's all.
I was tongue in cheek, but I'll just look in the rearview mirror. So this is 22 gigaflops, okay? That's shocking to me. So in 1998, some people maybe here weren't born then, but the first teraflop computer was delivered at Sandia. It cost $38 million, okay? So if you just look at the past, computing has always had a tremendous trajectory. And with mobile devices and computing, intimate part of our lives, I can't imagine really where it's going to be in 20 years. It'll be remarkable. It really will.
I was going to follow, actually I was going to say something along those lines. I think the biggest things that happen in computing are not projecting ahead from the things we already know how to do, but the new applications that are enabled by increases in computing power. So if you think about, deep learning, this was something that was well known and had been researched extensively for decades. That's right. But it wasn't until computing power crossed a certain threshold that it actually, and data became available, that it actually became practical, okay? And then, that's why the explosion was so rapid, was because all the foundation was already there intellectually, that caused it to happen when the engineering caught up. So, 1,000-fold increase in computing power probably enables something new that we aren't doing today, and I don't know what it is, but there's something like that will happen certainly within 20 years that will take us all by surprise.
Okay. Well, that brings us to the end. Thank you so much for for participating in this and being a good sport about the questions. Thank you all for coming.